Moving back to some more fundamental questions, because I mentioned before, I mean, our listeners are all smart and curious, but they're not all trained physicists. So I think we should devote just a bit more time discussing anti-de Sitter space on the one hand, and then conformal field theories on the other. And this is very basic, but what is the difference between positive and negative curvature of space?
Right. Well, let's start with flat space. So flat space is perhaps most intuitive because our universe around us can be approximated at least by flat space. Then when we have a positive curvature space-time, including time, that describes an expanding universe, so some universe with constant expansion rate. Our universe is now kind of similar to that at very large scales, and will become even more and more similar to that simplest constant expanding universe, sometimes called the de Sitter space. Now, an anti-de Sitter space is a universe that could be, well, it's time independent, so there is it's neither expanding nor contracting, but in some sense it expands when you go along the space direction. So if you go along a spatial direction, there is an expansion, let's say, of the time. Now, what this means in practice, a more pedestrian way, is to say that there is a kind of gravitational potential so let me explain this point a little better. So when we talk about curved space-time, what we mean in particular is that, for example, the flow of time in different locations could be different. So, for example, you are sitting right there, and there is some flow of time, let's say, in your chin, right? And there's time flows differently in the top of your head. And the reason that happens is that you are sitting in a gravitational field, and so time flows more slowly around your chin than on the top of your head. Now, this is a very, very tiny little effect that with the best clocks you could determine. I mean, with an atomic clock, the best ones can determine a height difference of a few millimeters, but it's a real effect.
And the difference is huge, though, between where we are now and the event horizon of a black hole, for instance.
Exactly, yeah. So that difference becomes more pronounced the more compact and heavy the object is. So if you at the horizon of a black hole, the difference is, if you wish, infinite. So the time at the horizon, with this definition of time, if you are just sitting at the horizon, not falling through the horizon, time is not flowing, and so the difference is infinite. So that's what happens. Now let's go back to anti-de Sitter space. So anti-de Sitter space, this is a very symmetric space, so you could be an observer sitting in anti-de Sitter space. And then what you would feel is that there is the time goes at a certain rate in your location, and if you go further out, it goes faster. And so you are like in the bottom of a big gravitational potential well. And if you throw any particle out, that particle will go out and then come back into where you are. So it's kind of the opposite of an expanding universe. In the expanding universe, you just throw out a particle, it will continue to go out and never come back to you. If you have, in this space, everything kind of concentrates things back to you. And it's similar to a gravitational potential well. The simplest version is you are sitting at the bottom of this gravitational potential well, and the gravitational potential grows and grows as you go further out, without bound, so that the particle can never escape. So it will always bounce back and get back to you. So that's roughly how one could think about it.
My understanding, though, is that when we think about anti-de Sitter space, it's in a please tell me if I'm wrong here. It's in a vacuum state, so there isn't mass in it. And would this mean, though, that at any point since it's so maximally symmetric, if at any point there were a particle and you threw it out, it would just come right back.
Yes, that's right. That's right. So if you're an observer just sitting freely, sitting freely in that space, if you throw a particle, it will come back to you. You might have a friend who you can also think about the point of view of that particle that got thrown. It's just it's falling also freely, and that particle sees that you went out, right? You went in some other direction, and then you meet again. So the description would be similar from your point of view and from the particle point of view.